Welcome to Dark Cosmos Theory. There exists a boundary in nature where our most trusted physical laws simply cease to function. This edge appears at roughly 1.616 multiplied by 10 to the negative 35th meter, a distance we call the Planck length. Beyond this threshold, our finest equations stumble and fall silent. Space-time itself transforms into something resembling flickering static rather than smooth fabric. Tonight, our journey takes us through this frontier with careful attention to detail. We'll explore what distance actually signifies when measurement tools become meaningless, investigate why concentrated energy forces tiny regions into collapse, and discover how atoms, electromagnetic radiation, and the cosmos all whisper identical restrictions. Find your comfortable position, allow your breathing to slow naturally, and let your mind remain alert while your physical form settles into rest as we embark on this contemplative expedition. If these explorations bring you moments of tranquility, a gentle gesture of support would carry profound meaning. The simple act of pressing like or tapping subscribe represents more than just emotion. It sends warmth across the digital void, confirming that curious minds still gather here to ponder and question. Each small action helps sustain this peaceful haven in the vastness, and your presence here fills me with genuine appreciation. Now, we ease into our first exploration. What actually fails when we attempt to observe ever smaller scales? Suppose we possess the ability to zoom inward without limit, traveling past atomic structures, beyond protons, even smaller than the tiniest quarks. Would the cosmos continue unveiling fresh layers indefinitely, or would everything simply dissolve into darkness? This question isn't mere speculation. It represents a genuine challenge that physics has wrestled with for over 100 years. Throughout history, whenever humanity constructed superior methods for examining the microscopic realm, from those earliest glass lenses through today's most powerful particle colliders, we've consistently followed one unchanging rule. Perceiving smaller structures demands higher energy levels. That's the fundamental mechanism at work. Electromagnetic radiation, like all wave phenomena, can only distinguish objects exceeding its own wavelength. The visible spectrum we perceive, that rainbow stretching from red through violet, possesses wavelengths measuring hundreds of nanometers in length. This width exceeds an atom's diameter by roughly 1,000 times. Consequently, even our most sophisticated optical microscopes fail to reveal atomic structures. Breaking through that barrier required scientists to employ electrons rather than photons. Electrons also exhibit wave properties, but theirs can be compressed to much shorter dimensions through acceleration to extreme velocities. Back in 1931, German physicist Ernst Ruska constructed the original electron microscope, demonstrating our capacity to peer far beyond visible light's limitations. By manipulating electron energy levels, he could shrink their wave patterns sufficiently to expose cellular organization, crystalline arrangements, and individual molecular structures. 3 decades forward, at California's Stanford Linear Accelerator Center, scientists pushed this concept toward its ultimate expression. They launched electrons at protons carrying tremendous energy, reaching tens of billions of electron volts. The scattering patterns from those electrons revealed something astonishing. Protons weren't solid spheres at all. They contained smaller constituents within them, quarks. That experiment, designated as deep inelastic scattering, became among the most significant discoveries in contemporary physics. It demonstrated that matter itself concealed another hidden layer. From that moment forward, we understood nature's simple rule clearly. Exploring smaller distances requires deploying higher energies. Wish to examine an atom's interior, you'll need energy measuring hundreds of electron volts. Desire to probe inside the nucleus? Billions become necessary. Want to observe what exists smaller than quarks? The required energy becomes nearly incomprehensible. But here emerges the paradox. When we concentrate increasingly vast amounts of energy into progressively tinier regions, we begin warping the very arena we're attempting to examine. Space-time itself starts bending. Einstein revealed to us that energy and mass represent two faces of identical currency. Packing excessive energy into minute spaces generates gravitational fields so powerful that space-time curves around them. Initially, this curvature remains gentle, practically imperceptible, but continue raising the energy levels. Keep attempting to zoom inward, and something remarkable occurs. The energy you've concentrated becomes so dense it collapses beneath its own gravitational weight. The region you're trying to observe vanishes behind an invisible barrier. Your microscope has effectively generated a miniature black hole. That represents the moment when the universe extinguishes the illumination. Past this threshold, no instrument can probe deeper because nothing, not even electromagnetic radiation, can escape the gravity you've created. Physicists can calculate this critical boundary. We call it the Planck length, approximately 1.6 times 10 to the negative 35 meters. This number defies comprehension through its sheer minuteness. For perspective, imagine enlarging a proton until it matched Earth's dimensions. Even then, the Planck length would remain smaller than a single atom on that planet-sized proton. At this scale, space and time abandon smoothness entirely. They ripple and oscillate like a boiling liquid, what physicist John Wheeler named quantum foam. Within this foam, the universe's geometry continuously twists, extends, and implodes. Our familiar concepts of distance and duration stop carrying meaning. Actually accessing this scale would demand energies approaching 10 to the 19th power giga-electron volts, a magnitude 15 orders beyond what the Large Hadron Collider achieves. Even constructing a particle accelerator spanning our entire galaxy wouldn't suffice. Nature appears to have erected a protective barrier around her deepest secrets. This isn't merely a technological constraint. It's fundamentally physical. The Planck length functions as a universal boundary, the smallest measurement unit possessing any meaning whatsoever. Below that threshold, the very concepts of space and time lose definition entirely. It marks the frontier where quantum mechanics and general relativity clash violently, and where some future unified theory of reality must eventually emerge. NASA's James Webb Space Telescope enables us to gaze backward through time, observing galaxies as they existed over 13 billion years ago. But when we direct our attention inward into matter's structure, we're also journeying through time, just in the reverse direction. Each layer we uncover brings us nearer to the physics governing the universe's earliest moments. At nuclear scales, we encounter echoes from the first seconds following the Big Bang. At quark levels, we touch the physics of the initial microseconds. And at the Planck length, we confront the very instant space-time itself emerged into existence. So what occurs when we attempt zooming beyond that boundary? Does space dissolve into pure chaos? Or does it unveil an even deeper organization, one our current theories cannot yet describe? Physicists from Einstein through Hawking have dedicated their existences to wrestling with that question. As John Wheeler once stated, at the Planck scale, space-time's smooth fabric surrenders to a quantum foam of subatomic turbulence. For now, we cannot reach it. But the Planck length stands simultaneously as both barrier and gateway, the boundary of everything we comprehend and the suggestion that something greater awaits beyond. And so, when we try zooming to infinity, the universe doesn't provide answers. It offers silence, a horizon drawn by its own fundamental laws. But if electromagnetic radiation itself cannot show us nature's smallest truths, perhaps something else can. Our next exploration examines why light fails to reveal atoms while electron beams succeed perfectly. If electromagnetic radiation serves as our primary means of perceiving the world, why does it fail when we attempt observing matter's fundamental building blocks? Why can't photons reveal atomic structures while electron beams can? Initially, this sounds paradoxical. We imagine light as truth's ultimate messenger, the carrier of every image we've ever experienced. From distant galaxies' glow through soft reflections on water droplets, light delivers the universe to us. Yet when scientists attempted using light to peer into atoms, they discovered nothing. The problem doesn't originate in our instruments. It exists within light's intrinsic nature. Every light ray behaves like a wave, and waves cannot reveal details smaller than their own wavelengths. The visible light reaching our eyes possesses wavelengths around half a micrometer, that equals 500 nanometers. But atoms measure approximately 1/10 of a nanometer across. So when we illuminate atoms with visible light, it's comparable to attempting to read fine print using swimming pool waves. The ripples simply wash over the details. To observe something that minute, we need significantly shorter waves, something with finer ripples, smaller crests and troughs. One might think we should simply employ higher energy light, like X-rays, and that's partially correct. X-rays, with their compressed wavelengths, can resolve atomic-scale structures. That's why X-ray crystallography became such a revolutionary tool. In 1912, Max von Laue directed X-rays at copper, sulfate crystals, and the resulting diffraction pattern revealed that atoms form precise repeating lattices. It birthed structural physics. But there's a complication. When photons reach that energy level, they no longer simply observe atoms. They begin destroying them. A photon, energetic enough to match an atom's scale, carries over 10,000 electron volts of energy, sufficient to ionize atoms, eject electrons, and potentially alter the crystal structure you're attempting to observe. That's where electrons enter the picture, not as light particles, but as matter behaving like waves. In the 1920 seconds, Louis de Broglie made a simple yet profound proposal. Every moving particle possesses a wavelength just like light does. The faster particles move, the shorter their wavelengths become. He called it the matter wave. 2 years later, this strange idea found verification. In 1927 at Bell Laboratories, Clinton Davison and Lester Germer fired electron beams at nickel crystals and observed diffraction patterns, patterns only waves can generate. It was as if electrons had transformed into light momentarily, rippling across the crystal's atomic grid. This single experiment revolutionized everything. It demonstrated that electrons, when accelerated to certain energies, could resolve atomic-scale structures. And the best part? They could accomplish this gently. An electron beam with merely a few hundred electron volts of energy has wavelengths small enough to distinguish atoms without vaporizing them. That's why electron microscopes soon replaced optical ones for studying matter's smallest details. In 1931, Ernst Ruska built the first electron microscope prototype in Berlin. His design employed magnetic lenses to bend and focus electron streams, generating magnified images of the microscopic world. Within just a few years, he could observe viruses, cell membranes, and molecular structures invisible to light. There's something almost poetic about how light, which illuminates the cosmos, remains blind to atoms, while electrons, the very substance of matter, can reveal their hidden geometry. The reason resides entirely in the relationship between energy and wavelength. To make light waves small enough, matching an atom's size, you need photons with energies around 12,000 electron volts, 1,000 times greater than visible light. But electrons moving with only a few hundred electron volts naturally possess wavelengths of the same order. So, for identical resolution, electrons need far less energy and therefore inflict far less damage. When you compare them, the difference feels almost unfair. A photon must fight harder, burn hotter, and risk destroying what it touches just to reveal what an electron can show with ease. Light, for all its glory, proves too coarse an instrument for the atom. That's why in contemporary laboratories, when scientists want to map atoms on surfaces or visualize molecular structures, they don't use light at all. They employ electron streams tuned with magnetic fields, scanned across samples at nanometer precision. The result isn't an image made of reflected light, but one constructed from interactions of waves scattering and interfering, painting pictures through probability. Modern transmission electron microscopes achieve resolutions reaching fractions of an angstrom, less than 1/10 of a nanometer. That's small enough to distinguish individual atomic columns in crystals. The smallest details we've ever resolved directly are on the order of a single hydrogen atom's diameter, and it all returns to one principle. Smaller wavelengths enable finer detail. But while we can keep shortening wavelengths, we can't do it forever because as wavelengths shrink, each probe's energy increases. And as we learned earlier, beyond a certain point, that energy bends space-time itself. If you keep trying to look closer, your act of observation eventually collapses into gravity. So the electron microscope represents a kind of middle ground, a balance between energy and delicacy. It's powerful enough to reveal atomic structures, yet gentle enough not to tear them apart. It stands as a quiet triumph of human ingenuity, proving we don't always need brute force to see deeper. NASA's own imaging technologies rely on similar principles. The James Webb Space Telescope, for example, sees in infrared longer wavelengths than visible light because it isn't trying to see smaller things, but fainter ones. Meanwhile, particle physicists on Earth use shorter and shorter waves, higher energies to peer into the subatomic world's fabric. Between these extremes lies a delicate continuum of vision, stretching from infinite galactic vastness to the infinitesimal decimal world of atoms. And in this continuum, light and electrons play different roles. Light tells us how the universe looks from outside, its shapes, colors, and motion. Electrons tell us how it's built from within, the hidden architecture of matter. Each has its limit, each its domain. It's worth remembering how counterintuitive this discovery was. When Davison and Germer first saw that diffraction pattern in 1927, they didn't believe it. Electrons were supposed to be particles, tiny bullets of charge, not waves of probability. But the pattern was undeniable. It looked exactly like light's interference fringes, and suddenly, the boundary between seeing and being began to blur. Richard Feynman later called this duality the central mystery of quantum mechanics. He said nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. That's the strange beauty of this story. When we tried using light to see matter, matter itself turned out to be a kind of light, a wave with its own frequency, its own pattern. And through that realization, we gained the ability to see what light never could. So why can electrons see atoms while light cannot? Because nature allows matter to reveal itself only through its own rhythm, through waves born of motion, not illumination. And that rhythm, at the atomic scale, belongs to electrons. But the closer we look, the more another mystery begins to rise. If atoms have structure, do their centers, the protons and neutrons themselves, also hide something deeper? If we could strike a proton hard enough, would it shatter, or would it reveal a hidden skeleton inside? That was the haunting question physicists faced in the late 1960 seconds. For decades, protons and neutrons had been treated as the solid heart of every atom, the indivisible bricks of the nucleus. But strange experimental hints began to whisper that these bricks might not be solid at all. Could there be something even smaller lurking within them? By that time, the periodic table had already been stripped down to its essentials. Atoms were mostly empty space, a tiny nucleus surrounded by an electron cloud. Ernest Rutherford had proved this in 1911 by firing alpha particles at thin gold foil and watching most pass straight through. Only a few bounced back, revealing that almost all of an atom's mass was concentrated in a nucleus just 100,000th its diameter. It was almost as incredible, Rutherford said, as if you fired a 15-inch shell at tissue paper and it came back to hit you. But now, more than 50 years later, scientists wanted to go deeper to ask whether even that dense nucleus was truly solid, or whether it too had an inner world. To find out, they would need to hit it with something far more precise than alpha particles, and with energies far greater than anything ever attempted before. The place that made this possible was the Stanford Linear Accelerator Center, known as SLAC, in California. Completed in 1966, it was a marvel of its time. A straight 2-mile-long tunnel designed to accelerate electrons to nearly light speed. By 1,960 standards, it was a machine of impossible ambition, a tool capable of probing matter's deepest layers ever accessible to humanity. Electrons were chosen for a reason. They are point-like with no known internal structure, and when they scatter off targets, they reveal the shape of what lies inside that target. In a sense, each high-speed electron is a tiny radar pulse of the subatomic world, an ultrafine probe that lets physicists map what cannot be seen. So the idea was simple but radical. Fire electron beams with energies of tens of billions of electron volts at protons and neutrons inside atomic nuclei and see how they scatter. If the nucleus were solid and uniform, electrons would scatter smoothly. But if the nucleus contained smaller pieces, electrons would bounce off in complex, irregular patterns. That was the logic behind what would become one of the most famous experiments in modern physics. Deep inelastic scattering. Inelastic because the collisions weren't gentle. Electrons didn't just glance off surfaces. They struck so hard that they transferred energy, shaking protons apart. When the data first came in around 1968, it didn't fit expectations of a solid sphere at all. Electrons didn't bounce as if the proton were a single lump. Instead, they scattered in sharp, point-like bursts, as if the electron beam were ricocheting off smaller targets hidden inside. Those patterns told a story no one could ignore. Inside every proton, there seemed to be 3 smaller concentrations of charge, 3 points of resistance that deflected electrons most strongly. These became the first experimental evidence for quarks, the hypothetical particles proposed just a few years earlier by Murray Gell-Mann and George Zweig. Gell-Mann had coined the term quark in 1964, borrowing it from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark. It was a whimsical name for what was at the time a purely mathematical concept. No one had actually seen a quark. They were introduced to explain the bewildering zoo of particles emerging from earlier experiments. But now the SLAC data made that idea real. The conclusion was stunning. Protons and neutrons, once thought to be the final solid units of matter, were in fact composite structures, each made of 3 quarks bound tightly by powerful forces. These forces would later be described by a new theory, quantum chromodynamics, or QCD, the theory of the strong nuclear force. The strong force, it turned out, is unlike any other. It grows stronger as you try to pull quarks apart, like a rubber band that stretches but never breaks. The energy needed to separate quarks is so great that it spontaneously creates new pairs of quarks before the originals can be freed. That's why no one has ever isolated a single quark. They are forever confined within hadrons, protons, neutrons, and other particles made of 3 or 2 quarks. This discovery completely changed our understanding of matter. The nucleus, far from being solid, is mostly space-threaded by energy fields. Quarks, dancing inside a dense cloud of gluons, the carriers of the strong force. These gluons continually appear and vanish, exchanging energy at speeds close to light. If we could somehow look inside a proton, it wouldn't look like a hard sphere at all. It would look alive, a flickering storm of quantum motion, a sea of virtual particles colliding and dissolving billions of times per second. Experiments since SLAC have refined this picture with extraordinary detail. At CERN and Fermilab, particle accelerators smashed protons together at higher and higher energies, confirming that quarks behave as nearly free particles when struck at very short distances, a property called asymptotic freedom. But as their separation grows, the strong force tightens again, drawing them back into confinement. This behavior is unique in physics. Most forces like gravity or electromagnetism get weaker as objects move apart. The strong force does the opposite. It ensures that quarks can never escape the prison of their own creation. And yet this confinement is the reason matter is stable. The strength of the strong force holds protons together for billions of years, longer than the age of the universe itself. It is the reason atoms exist, the reason stars burn, and the reason you listening to this now are still here. The energy scale needed to probe such depths, around 1 billion electron volts, corresponds to distances of about 1/4 of a meter. At that level, the distinction between solid and empty begins to blur. Matter, it seems, is mostly made of nothing except for the energy that binds nothing into something. Even today, Slack's legacy remains one of the most elegant examples of how we learn by scattering. We throw particles at particles and read the universe in the way they recoil. It's like striking a bell in the dark and listening to its echoes to learn what it's made of. And yet, even the quark might not be the final layer. Some physicists suspect there could be smaller entities, prions hidden beneath, though no evidence yet confirms this. The search continues, but each step deeper demands energies far beyond our reach. As physicist Richard Feynman once said about the SLAC results, we found that the world is more complex and more interesting than anyone dared imagine. That statement still holds true. Every time we peel back one layer of nature, we find a deeper mystery waiting. And as our machines grow stronger, so do the questions. If we keep raising the energy, keep colliding protons harder and harder, will we eventually reach a limit where even the strong force gives way to something new? That's the next frontier. When our instruments reach the scale of trillions of electron volts, do we just see more quarks or something stranger still? What happens when you build a machine so powerful it can tear open the vacuum itself? Can it really see reality's hidden layers, or only disturb them for a fleeting instant before they vanish again? That's the question behind the Large Hadron Collider, or LHC, the most ambitious scientific instrument ever built. Many imagine it as a weapon, or as a ring of unimaginable energy buried beneath the French-Swiss border. But in truth, the LHC is a kind of microscope, a gigantic quiet eye that doesn't use glass or lenses, but magnetic fields and protons moving at nearly light speed. Its goal is simple in concept, but almost impossible in execution: to look deeper than any human eye has ever seen. The LHC accelerates two proton beams in opposite directions around a circular tunnel 27 kilometers long. Each beam carries particles energized to about 7 trillion electron volts. 7 tera-electron volts, or 7 TeV. When they collide head-on, the total energy of the crash reaches 14 TeV. That number is not random. It was chosen because it sits near a theoretical threshold, a scale of energy where the Higgs field, the invisible field that gives mass to matter, can be shaken hard enough to produce a ripple, the Higgs boson. This is what physicists mean when they say the LHC can see the Higgs. It's not looking at the field directly. It's tapping it like striking the surface of a pond to reveal a single fleeting wave. When those protons collide, their energy compresses into a point smaller than an atom's nucleus, recreating conditions that last existed less than a trillionth of a second after the Big Bang. For a moment, the vacuum of space itself behaves differently. Particles appear and disappear. Energy converts to mass, and mass back to energy. The same processes that once shaped the newborn universe. But to understand why the LHC is really a microscope, not just a collider, we need to remember one rule that connects all scales. The higher the energy, the smaller the distance you can probe. This is the guiding principle of modern physics. Every increase in energy sharpens our vision of the microscopic world. When we used visible light, we could see cells. When we used electrons, we saw atoms. When we used GeV-level beams, we saw quarks. And now, with TeV-level energies, we can disturb the very fields that make those quarks possible. Inside the LHC, each proton is guided by 1,232 superconducting magnets, cooled to about 1.9 Kelvin, colder than the temperature of outer space. The vacuum inside the beam pipe is emptier than the void between stars. Every component, every pulse, every magnetic bend is designed to keep those beams aligned to within a fraction of a millimeter. When they finally collide, they do so in detectors the size of buildings: Atlas, CMS, ALICE, and LHCb. Enormous instruments built not to destroy, but to listen. Atlas and CMS, the twin giants of the LHC, are what allowed physicists to detect the Higgs boson in 2012. Each collision event is recorded by millions of sensors. Out of more than 1 billion collisions per second, only a few rare ones produce the telltale decay patterns that signify a Higgs. And even those traces exist for less than 1/trillionth of a second before dissolving into other particles. When the Higgs boson was confirmed, Peter Higgs himself said softly, "It's really an incredible thing that it has all come true." It was not just a discovery. It was proof that the Standard Model, the framework describing all known particles and forces, was complete in one profound sense. But the deeper question remains: how deep is the LHC really? How fine is its resolution? If we treat it as a cosmic microscope at 14 TeV, the LHC can probe distances down to about 100 billionth of a meter, 1/10 of a femtometer. That's smaller than a proton's radius, approaching the scale where quarks and gluons swirl in confinement. At this level, we are not just looking at particles anymore. We are exploring fields, continuous backgrounds that permeate all of space. The Higgs field, the electromagnetic field, the strong and weak nuclear fields, they are not things that exist inside space. They are space in motion. Each collision at the LHC shakes those fields, revealing how they interact. Yet, for all its power, the LHC is still far from the energy needed to see the Planck scale, the ultimate limit we discussed earlier. To reach that, we'd need to boost protons not to 7 TeV, but to 10 billion trillion TeV, a machine the size of a galaxy. So the LHC is not the final microscope, it is a bridge. The sharpest tool we currently have between the known and the unknown. Its discoveries reach beyond physics, into the very structure of our understanding. Because when you push energy high enough, you don't just see smaller things, you create new ones. That's what makes the LHC so different from any microscope before it. It doesn't only observe the world, it briefly recreates it piece by piece from pure energy. The detectors record these moments with astonishing precision. Each proton-proton collision releases jets of particles, photons, and neutrinos. Sophisticated algorithms then trace those fragments backward, reconstructing what happened at the instant of impact. It's as if you dropped a watch onto the floor, heard the pieces scatter, and then deduced the watch's shape from the sound alone. The data are so complex that they require computing systems distributed across the world. The worldwide LHC grid, connecting hundreds of institutions in over 40 countries. Each second of collision produces more data than an entire human lifetime of internet traffic. Every bit of it is filtered, analyzed, and compared against the predictions of theory. This collaboration of thousands of scientists represents one of humanity's quiet triumphs: cooperation at planetary scale to understand the tiniest pieces of existence. There's something quietly moving about that. Not poetic, but profound in its precision. In the years since the Higgs discovery, the LHC has gone further. It has searched for supersymmetric partners, heavier cousins of known particles predicted by certain extensions of the Standard Model. None have yet been found. It has examined rare decays, hunted for hints of dark matter, and measured the strong force between quarks at unprecedented energies. Every run brings refinements, upgrades, and higher luminosity, more collisions per second, sharper data, deeper insight. The upcoming high luminosity LHC will multiply its reach even further, revealing whether nature hides surprises at scales we haven't yet glimpsed. But beyond the technical mastery, there's a quiet question that lingers in every control room at CERN. If we've now seen the Higgs, what's next? If the Standard Model is complete, why does the universe still feel unfinished? With dark matter, dark energy, and gravity itself still standing apart? Maybe the answer lies just beyond the reach of 14 TV. Maybe we need to go higher, to the hundreds or thousands of TV, to see the next threshold, the next hidden layer of reality. Or maybe the clues are already in the data, waiting to be noticed. As CERN physicist Fabiola Gianotti said after the Higgs discovery, "We have reached a milestone, but it is a new beginning." And indeed, that's what the LHC is. Not an end, but a doorway. The sharpest eye humanity has built. One that looks not through glass but through energy. A machine that lets us watch the universe replay its opening act, one collision at a time. But what happens when even this enormous energy begins to push against a deeper law? When our effort to see more causes gravity itself to push back? What if the closer we look into the universe, the more the universe pushes back? What if, instead of revealing new details, nature itself begins to collapse under the weight of our curiosity? This is not imagination. It is the quiet revenge of gravity, a limit built into space-time structure itself. At first glance, it sounds strange. How could simply looking too closely create a black hole? But that's exactly what happens when observation energy becomes too intense. Let's begin gently. Every attempt to see smaller structures requires more energy. To probe the atom, we need electron beams accelerated to hundreds of electron volts. To peer inside the nucleus, we use energies of billions. The rule is simple. Finer details demand shorter wavelengths, and shorter wavelengths come from higher energy. But here's where the universe turns that rule against us. The more energy we focus into a small region of space, the more that energy itself curves space-time. Einstein's general relativity tells us that energy, just like mass, creates gravity. So every time we push our microscope to higher power, we also strengthen the gravitational field inside the region we're observing. At first, the effect is tiny, completely negligible. But as we push beyond atomic scales into the realms of quarks and gluons, energy density grows to unimaginable levels. Eventually, a strange balance emerges. The energy we use to probe a region becomes so concentrated that the gravity it creates traps light itself. The region we're trying to observe forms its own event horizon. That's the counterattack of gravity. The moment when looking too closely makes everything vanish. Physicists can describe this in simple terms. If you compress enough energy into a small enough space, that region behaves as if it has mass. And if the gravity from that mass becomes strong enough, it forms a boundary, a radius within which light cannot escape. That's the Schwarzschild radius. When the size of the region you're trying to examine shrinks down to the same scale as this radius, the game is over. Your microscope becomes a black hole. At that threshold, adding more energy doesn't help you see smaller. It just makes the black hole bigger. This is the cosmic version of diminishing returns, the ultimate limit of observation. It tells us there's a smallest meaningful length in nature, around 1.6 times 10 to the negative 35th meters, the Planck length. At that scale, the gravitational radius of the energy equals the region itself. Any attempt to focus harder collapses the experiment. To put it in perspective, the protons inside the Large Hadron Collider reach energies of about 7 trillion electron volts, probing distances down to a tenth of a femtometer. To reach the Planck length, you'd need energies a trillion times greater, 10 to the 19th giga-electron volts. That's more energy than all the power produced by every star in the observable universe, focused into a single point. So the universe protects its smallest scales behind a gravitational curtain. The closer we look, the stronger that curtain pulls shut. It's not a failure of our technology, it's a fundamental property of spacetime itself. Physicists sometimes describe this interplay as a duel between quantum mechanics and gravity. Quantum mechanics encourages us to look closer, to sharpen our measurements, to localize energy. But gravity punishes that ambition. It says the more you concentrate energy, the more space-time bends until the concept of position itself disappears. At first, this idea was just a theoretical curiosity, but it has profound consequences for the way we think about the universe. It means there is a boundary not just of what we can build, but of what can exist. Beyond that limit, physics as we know it cannot describe what happens. To get a feeling for how small this limit really is, imagine zooming in on a proton. Now imagine zooming 1,000,000,000,000 times further. You're now at the Planck scale where distances lose meaning, where time and space fluctuate like foam. At this point, gravity and quantum effects are equally strong, and neither can be ignored. This threshold, where energy, gravity, and measurement collide, is sometimes called the black hole barrier. No matter what technique we use, any attempt to see beyond it triggers gravitational collapse. The act of observation creates the very wall it cannot cross. And this isn't just theory. The same logic explains why black holes in space have event horizons. When a massive star collapses, its mass is compressed into such a tiny volume that its gravitational radius exceeds its physical size. Light can no longer escape, and the star's core disappears behind a horizon. In our case, the same principle applies not to stars but to experiments. In 1976, physicist Kip Thorne described this elegantly. The closer you get to the interface of gravitational radius, the more violently the laws of physics resist your intrusion. That resistance is what defines the Planck scale. It's not a wall in the ordinary sense. Nothing physical is blocking the view. It's a limit in the very geometry of reality. Distances, time intervals, even the distinction between inside and outside lose their meaning there. In this sense, gravity's counterattack is not destructive, but protective. It prevents us from tearing the universe apart by accident. It ensures that energy, matter, and space-time remain balanced. And yet, this limit also leaves us with an unfinished story. Because if we can't see what happens beyond that boundary, how can we ever know what space-time is made of at its core? Are we forever trapped outside the deepest layer of reality? That question is what drives the search for a theory of quantum gravity, an idea that would unite Einstein's relativity with quantum mechanics. The hope is that such a theory will describe how space-time behaves when it becomes as small and turbulent as the particles it contains. Some think it might look like a network of discrete loops, the spin networks of loop quantum gravity. Others imagine vibrating strings, tiny filaments whose oscillations replace the chaos of collapsing space-time. But until such a theory is complete, we must live with the paradox. The smaller we look, the more gravity bends our window shut. The harder we try to see the foundations of the universe, the more the universe hides them. Still, this balance between energy and gravity, between curiosity and collapse, is what makes the cosmos stable. It's the quiet law that keeps the stars from imploding and the atoms from tearing apart. It defines not just a limit of knowledge, but the architecture of existence itself. As Stephen Hawking once noted, the closer you get to a black hole, the more time slows down until it stops entirely at the horizon. At the Planck scale, perhaps time itself pauses, not because we reach the end of space, but because the act of measurement loses meaning. And yet even this gravitational counterstrike gives rise to one of the most fascinating frontiers in modern physics, the place where quantum theory and gravity must finally meet. Because if space-time collapses when we look too closely, what happens when quantum uncertainty is also taken into account? Is there a smallest possible size in the universe, a scale beneath which distance itself stops making sense? Physicists call that frontier the Planck Length, the line where the laws of nature as we know them begin to unravel. It's not simply a matter of smaller rulers or more powerful microscopes. It's a question of whether the concept of space can even exist below a certain scale. To understand why, let's trace how this strange number, about 1.6 times 10 to the negative 35th meters, was born. It didn't come from experiment or measurement, but from pure reasoning. When physicists combined three of nature's fundamental constants, the speed of light, the gravitational constant, and Planck's constant of quantum action, they found that these values naturally combine into a single unit of length. That number marks the scale where both quantum mechanics and gravity become equally strong. Below it, neither theory can describe what happens. Einstein's smooth spacetime from general relativity and the restless probabilities of quantum theory collide and both fail. To visualize how small this really is, imagine shrinking yourself down step by step. A human hair is about 1/10 of a millimeter wide. A red blood cell is 1,000 times smaller. A proton is 10 billion times smaller than that. Now keep dividing that proton's diameter by 10 billion again, and then again 30 times in a row. That's the Planck length. At that point, space is no longer a quiet fabric. It churns and flickers, its geometry twisting under quantum uncertainty and gravitational tension. The distances between points blur. The very meaning of before and after becomes uncertain. John Wheeler, one of Einstein's last collaborators, called it quantum foam. In this foam, space-time is not continuous, but dynamic, alive, and unstable. Tiny wormholes open and close in trillionths of a second. Energy fluctuates violently, creating brief bursts of curvature that rise and vanish like bubbles in boiling water. What we think of as empty space at human scales is, at the Planck scale, a storm. The energy required to reach such scales is beyond imagination. It's called the Planck energy, roughly 10 to the 19th giga-electron volts. For comparison, the Large Hadron Collider, the most powerful machine on Earth, reaches only 14 tera-electron volts, 15 orders of magnitude smaller. To build an accelerator that could reach the Planck energy, it would have to be as large as several thousand light-years across. Not impossible, just for technology, but impossible by the very structure of the universe. This limit isn't just about engineering. It's a limit of principle because at those energies, the gravitational pull of the energy itself would instantly collapse into a black hole. The moment you tried to measure something smaller, space-time would fold shut around it. Nature draws a curtain not of matter, but of meaning. Physicists have long debated what this curtain represents. Some see it as a wall, the smallest unit of space, like pixels in a cosmic screen. Others see it as a threshold, a smooth transition into an as-yet unknown realm where gravity and quantum theory merge. Either way, it's the scale where our mathematics begins to whisper, "You can't go any further." It's almost poetic in its precision. From the Planck length, we can also define the Planck time, the shortest possible moment that can be meaningfully measured, about 10 to the negative 44 seconds. Below that, the sequence of cause and effect blurs. Time ceases to flow in the way we understand it. These scales mark the earliest possible chapter of the universe. The moment just after the Big Bang, before the laws of physics froze into their familiar forms. NASA's and ESA's missions, from COBE to WMAP to the Planck satellite, have mapped the afterglow of that moment, the cosmic microwave background. But they can only look back to when the universe was about 300,000 years old. The Planck era, by contrast, ended when the universe was less than a trillionth of a second old. At that time, everything we know, matter, energy, even the geometry of space, was still tangled together. Forces had not yet separated. The Higgs field had not yet condensed. The universe itself was smaller than an atom, yet contained the seeds of all future galaxies. The Planck scale, then, is not just a number. It's the edge of our cosmic memory. It's where the known laws break down and something deeper begins. To go beyond it, we need new physics. That's why theories like string theory and loop quantum gravity exist. They are not guesses born of imagination, but attempts to describe what happens when space-time stops being continuous. String theory replaces points with tiny vibrating loops of energy, each about the size of the Planck length. Loop quantum gravity, on the other hand, suggests that space itself is built from discrete units. little quanta of area and volume connected in a network. Both theories, despite their differences, agree on one profound thing. Below the Planck scale, distance itself ceases to be a measurable quantity. You can't say something is half a Planck length apart any more than you can have half of a photon. It's not just too small to measure, it's undefined. That makes the Planck length not a wall we can climb, but a horizon we can never cross, a fundamental boundary between what can exist and what can only be imagined. It's the smallest tick on the ruler of reality. Yet, there's a quiet irony. The constant that defines the Planck length, the gravitational constant g, is also the least precisely measured of all fundamental constants. We know the speed of light and Planck's constant with exquisite precision, but gravity still eludes our measurements, which means, in a strange way, the most fundamental scale in physics depends on the one constant we understand the least. Still, the idea of a minimal length has practical consequences. It means there's a limit to how much information the universe can store in a given space. According to the holographic principle, the total information inside a region is proportional not to its volume, but to its surface area measured in Planck units. In other words, reality might be pixelated at the Planck scale, each pixel carrying one bit of information. This idea underlies modern black hole physics. When Stephen Hawking discovered that black holes radiate energy, the rate of that radiation turned out to depend on the Planck area, the square of the Planck length. It was the first hint that the universe, at its deepest level, may count information in Planck-sized pieces. So is the Planck length truly the end of reality, or just the beginning of something deeper? For now, we cannot say. It's the smallest scale we can define. But whether nature actually quantizes space, there remains one of the most profound open questions in science, and it's a humbling thought. Every measurement, every observation, every law of physics rests on the assumption that space and time are continuous. But if they're not, if they're built from discrete Planck-sized building blocks, then our entire view of the universe is only an approximation. As physicist Carlo Rovelli once said, at the Planck scale, space is not continuous. It's made of quanta. The world is woven from loops of gravity. It's a quiet reminder that beneath the smoothness we see lies a granular, vibrating foundation. And if the Planck length is indeed the last wall of the visible world, what lies beyond that wall might not be smaller, but entirely different. Perhaps space and time themselves are just emergent properties of something else, something more fundamental. Which brings us to the next mystery. If there is a minimum distance, does the famous uncertainty principle itself change when gravity joins the game? If every photon we use to measure a point in space also bends that space itself, then what does precision even mean? That is the heart of one of the most delicate puzzles in modern physics, the search for how quantum uncertainty changes when gravity enters the equation. It all begins with a principle so fundamental that it reshaped science itself. Heisenberg's uncertainty principle. In the 1920 seconds, Werner Heisenberg realized that in quantum mechanics, you can never know both the position and momentum of a particle with perfect accuracy. The more precisely you pin down where something is, the more uncertain its motion becomes, and the more precisely you measure its momentum, the blurrier its position grows. The universe at its smallest scales refuses to stand still under observation. This is not a limit of our instruments, it's a property of nature itself. Even in a perfect laboratory, even with infinite skill, the uncertainty remains. It's as if reality hides its coordinates behind a soft veil of probability. But Heisenberg's principle, elegant as it is, was written for a world without gravity. It describes the quantum domain, where energy and probability dance, but where spacetime's geometry stays fixed. Once we invite gravity in, once we allow energy itself to bend the stage it plays on, that balance begins to break. Imagine you're trying to locate an electron with light. You shine a photon on it, a particle of light with a certain wavelength. If you use light with a long wavelength, You can't see details smaller than that wave size, so you choose shorter and shorter wavelengths, higher energy photons to get a sharper image. But at some point, your photon becomes so energetic that its own gravity begins to matter. That single photon now carries enough energy to distort space-time ever so slightly around the region you're observing. The act of measurement bends the very coordinates you're trying to measure. If you keep pushing to higher energies, the distortion grows. Eventually, the photon's energy density becomes so extreme that it would create a tiny gravitational well, a miniature black hole forming, right where you tried to take a measurement. Instead of seeing more detail, you lose everything. This idea leads to what physicists call the generalized uncertainty principle, or GUP. It says that Heisenberg's uncertainty rule must be modified when gravity becomes strong. At small energies, the usual quantum behavior dominates. The more you know a particle's momentum, the less you know its position. But as you increase energy, and therefore gravitational influence, something new happens. The uncertainty in position stops shrinking. It reaches a minimum and then begins to grow again. In other words, there is a smallest measurable distance in the universe. A point where trying to look closer actually makes your vision blurrier. That minimum distance matches the Planck length, about 1.6 times 10 to the negative 35th meters. A result reached not by cosmology, not by high-energy colliders, but by pure reasoning about how measurement, energy, and gravity interact. The beauty of this idea is that it connects two of the most powerful theories in science without forcing them to merge. From the quantum side, Heisenberg gave us a law about limits of precision. From the gravitational side, Einstein told us that energy bends space-time. The generalized uncertainty principle is where those two truths meet, softly, mathematically, and inevitably. It means that even if we never build a machine powerful enough to reach the Planck energy, nature has already built its own safeguard, the fabric of space-time itself. It won't allow us to squeeze information into a region smaller than that scale. This gravitational upgrade of Heisenberg's principle has inspired decades of research. In string theory, for example, it appears naturally. Strings, the fundamental filaments that replace point particles, resist compression. The more energy you pump into them, the more they stretch and vibrate, spreading out instead of shrinking. Once again, nature protects its smallest domain from collapse. Even in loop quantum gravity, a theory that quantizes space itself, a similar result emerges. Distances and areas come in discrete units, indivisible quanta, each roughly the size of the Planck length. Below that, geometry simply doesn't exist as we understand it. You might think this sounds purely theoretical, far beyond anything measurable, but its fingerprints appear subtly in black hole physics. When Stephen Hawking derived the radiation emitted by black holes, he found that their temperature and entropy depend on surface area measured in Planck units. That link between information, gravity, and quantum uncertainty may be a clue that the GUP is not just mathematical but physical. It also changes how we think about information itself. If there is a smallest possible length, then there is also a smallest unit of information, a quantum bit tied to that scale. Every black hole, every region of space, carries a finite number of bits proportional to its surface area. As physicist Jacob Bekenstein put it, the universe stores information not in its volume, but on its boundary. This simple statement connects black holes, holography, and quantum uncertainty, three of the deepest threads in modern physics, all converging on the same idea. There is a natural limit to knowledge. Not because we lack tools, but because reality itself is built that way. To illustrate just how strange this limit is, consider an experiment. Suppose you try to measure the position of a particle with extreme precision. You use higher energy light, shorter wavelengths, and better detectors. Initially, your accuracy improves. But beyond a point, as you raise the energy further, the gravitational field of your measuring photon bends the particle's path. introducing new uncertainty. Eventually, if you go far enough, you'd create a gravitational horizon around your own experiment. It's as if the act of asking where creates a ripple so strong that space refuses to answer. NASA and ESA's work in observational cosmology echoes this idea on much larger scales. When the James Webb Space Telescope looks at distant galaxies, it's also probing space-time structure, how light stretches as the universe expands. On the opposite end of scale, theoretical physicists do something similar with thought experiments, stretching the laws of measurement to their breaking point. Both kinds of exploration, the cosmic and the quantum, meet at the same question. Is there a smallest pixel of space? The generalized uncertainty principle suggests yes, but not as a hard wall. It's more like a horizon of fuzziness where the clarity of position and momentum trade places, blending into each other. At that edge, the universe is neither continuous nor discrete, neither smooth nor rough. It's something in between. Heisenberg himself could never have guessed that his principle would one day touch the physics of black holes. Yet, here we are, tracing the same uncertainty he discovered in electrons to the very structure of space-time. As physicist Lee Smolin once said, "The quantum is not a theory of things, it's a theory of relationships." And when gravity joins that network of relationships, uncertainty becomes more than just a blur. It becomes the architecture of reality. But if there's a smallest measurable distance, then what about the very substance of what we're measuring? If matter is made of waves and space itself may be quantized, could the building blocks of reality be something more than points? If particles aren't points at all, but tiny vibrating strings, does the idea of infinite sharpness still mean anything? That's the question that gave birth to one of the boldest theories in modern physics, string theory. By the late 20th century, scientists had already reached the limits of their equations. Quantum mechanics ruled the small, general relativity ruled the large. But between them, at the Planck length, both began to break. Every attempt to merge them led to infinities. Impossible numbers that said, quite literally, the universe couldn't exist the way our math described it. The problem wasn't in our telescopes or colliders, it was in our picture of matter itself. In all of physics up to that point, elementary particles were treated as points. Zero-dimensional dots with no size, no shape, just position and charge. That simplification worked beautifully for most of nature. But at ultra-high energies, the scales near the Planck length, it caused a crisis. Because when two point-like particles collide, all their energy is focused into an infinitesimal point. The mathematics explodes. Gravity becomes infinite. So what if, physicists wondered, the fundamental objects weren't points at all, but strings? One-dimensional filaments, incredibly small, about the size of the Planck length, 10 to the negative 35 meters. If particles were vibrating loops instead of dots, the infinities might vanish. The energy would be spread along the string's length, never collapsing into a singular point. And it worked. When theorists replaced points with strings, the infinities disappeared. Gravity, instead of breaking the equations, emerged from them naturally. That was the revelation. In string theory, gravity isn't added by hand. It's a built-in consequence of how strings move. At ordinary energies, strings behave like particles. Their vibrations are so small that they appear point-like to us. But as you pump in more energy, as you zoom in, the picture changes. Instead of becoming sharper, the strings begin to vibrate more violently, sprouting new modes of motion. Their effective size expands. It's a perfect echo of what we saw with gravity and the generalized uncertainty principle. When you try to measure too precisely, the very act of adding energy blurs the picture. String theory takes that blurring and builds it into the foundation of matter itself, at extremely high energies, far beyond any collider we can build. A string can't be squeezed smaller than its own length. The more energy you add, the more it stretches, vibrating into higher and higher modes. Like a guitar string tightening under tension, the resolution stops improving. Nature simply refuses to let you see finer detail. This leads to a remarkable idea. There is a minimum measurable distance in string theory, roughly equal to the string's length itself, close to the Planck scale. Below that, the word distance loses meaning, not because space ends, but because the tools we use to define space stop working. The story of how this idea unfolded is as human as it is scientific. String theory didn't begin as a theory of everything. It began in the late 1960 seconds as a model to explain the strong nuclear force, the force that binds quarks inside protons. Physicists working on particle collisions saw that the patterns of energy they measured could be described by the vibrations of a tiny string. But soon something unexpected appeared in the math, a vibration mode that behaved exactly like a graviton, the hypothetical quantum particle of gravity. That single detail changed everything. Suddenly, string theory wasn't just about the strong force. It was about all forces. It could include electromagnetism, the weak and strong nuclear forces, and gravity itself, all woven together by the geometry of vibrating strings. Each vibration of the string corresponds to a different particle, much like the notes of a violin correspond to different sounds. The electron, the photon, the Higgs boson, all could be different harmonics of one underlying structure. As physicist Brian Greene beautifully put it, the universe is a symphony of vibrating strings, and the laws of physics are the melodies they play. The idea may sound poetic, but its implications are rigorously mathematical. String theory requires extra dimensions, not just the 3 of space and 1 of time, but up to 10 or 11 in total, curled up so tightly that we can't see them. These hidden dimensions determine how the strings can vibrate, and therefore what kinds of particles exist in our universe. The shapes of those hidden dimensions are called Calabi-Yau manifolds, intricate geometric structures that fold and twist in ways far beyond human intuition. Each possible shape corresponds to a different version of the universe, with its own laws of physics. Theorists estimate there could be 10 to the 500th power of such possible shapes, a number so large it defies imagination. At this point, string theory becomes more than a fix for infinities. It becomes a vast landscape of possible realities. And yet, at its heart, it still answers a simple, profound question. Why can't we zoom in forever? Because in a world made of strings, infinite sharpness is an illusion. The string's own length defines the smallest possible scale. Beyond that, new energy doesn't reveal new detail. It simply excites new vibrations, new resonances. The picture doesn't sharpen, it sings. This built-in softness is what saves the fabric of reality from tearing itself apart. In point particle theories, collisions at infinite energy lead to infinities in curvature, singularities. In string theory, those singularities are smoothed away by the finite size of strings. The energy never concentrates into a single point, so space-time never collapses, and from that smoothing, gravity itself emerges naturally. When strings interact and vibrate, one particular mode behaves exactly like the gravitational field described by Einstein. It's not an extra ingredient, it's an inevitable outcome. That's why physicists often say that in string theory, Einstein's gravity falls out of the math. The universe doesn't need gravity added to it. It's already there, encoded in the motion of every string. This insight brings a rare harmony to physics. For the first time, quantum mechanics and gravity coexist peacefully, not as rival frameworks, but as aspects of the same geometry. Space, time, energy, and vibration all become one language. Of course, we have yet to test this directly. The energies required to observe strings, on the order of the Planck scale, are far beyond any human experiment, but indirect evidence may one day appear. Subtle patterns in the early cosmic microwave background, ripples in space-time from the early universe, or exotic particles predicted by supersymmetry might offer glimpses of this hidden structure. Until then, string theory remains a masterpiece of unification, a theory not yet proven, but astonishingly consistent. It gives us a framework where the smallest scale is not chaos, but music, where the deepest layer of the universe is not a wall, but a rhythm. As theoretical physicist Edward Witten once said, string theory is not just a theory of strings. It's a framework that contains gravity and quantum mechanics as part of a larger whole. And that larger whole may finally explain why spacetime does not tear when we probe too deep, why nature's smallest details shimmer instead of shatter. But there's another possibility, one even stranger than strings vibrating in 10 dimensions. What if space itself is not continuous at all, but made of discrete quantum building blocks, tiny chunks of area and volume woven together by the spin of spacetime? What if the smooth fabric of spacetime, the one Einstein described so beautifully, isn't smooth at all? What if beneath everything we know, the universe is woven from discrete quantum threads? A cosmic lattice, granular and finite? That is the daring question behind one of the most fascinating theories in modern physics. Loop quantum gravity. It begins not with strings or vibrations, but with geometry itself. Where string theory treats the universe as a symphony of energy, loop quantum gravity treats it as a network of quanta of space. To understand why this idea matters, we have to revisit a problem Einstein left unsolved. His general theory of relativity tells us that gravity isn't a force pulling at a distance. It's the curvature of spacetime caused by mass and energy. Planets move along the curves, and light bends through them. Everything flows smoothly in that elegant geometry. But when you zoom down to the smallest scales, to the Planck length, about 1.616 times 10 to the negative 35th meters, that smoothness begins to crumble. Quantum fluctuations shake spacetime like ripples on a restless sea. The continuous surface Einstein described no longer holds. Loop quantum gravity, or LQG, takes that breakdown seriously. It doesn't try to unify gravity by adding new particles or extra dimensions. Instead, it rewrites the very idea of space. According to LQG, space is not continuous, it's quantized. Just as light comes in discrete packets called photons and energy comes in quanta, space itself comes in tiny, indivisible units, the smallest possible chunks of area and volume. These are unimaginably small, each roughly the size of the Planck scale. In this picture, the geometry of spacetime is made of a network called a spin network. Each node of the network represents a quantum of volume, and each link between nodes represents a quantum of area. Together, these form the microscopic scaffolding of the universe. When viewed from afar, this network looks smooth, just as a beach looks smooth from a distance, even though it's made of countless grains of sand. But up close, the continuity dissolves into discrete, vibrating units. It's a radical but elegant idea. Space is built from loops. Closed loops of gravitational field lines weave together, forming a fabric of finite, interconnected regions. Time, too, is quantized, progressing in tiny jumps instead of a continuous flow. Reality at its deepest level ticks like a quantum clock. Carlo Rovelli, one of the founders of LQG, explains it simply. At the Planck scale, space is not continuous. It is made of grains. The world is woven from loops of gravity. This isn't just poetic imagery. The theory is built on rigorous mathematics. Using Einstein's equations reformulated in quantum form, physicists found that areas and volumes can only take on discrete values. Much like how the energy levels of an electron in an atom are quantized, you can't have a fraction of a quantum of volume. That means even empty space is made of structure. A quiet web of quantum geometry that sets the stage for everything that exists. Space is not nothing, it is something with its own atomic texture. At larger scales, this texture averages out, giving rise to the smooth spacetime of general relativity. So remarkably, Einstein's theory isn't thrown away. It's recovered naturally from the quantum behavior of these loops when you zoom out. In the language of physicists, general relativity emerges as the low-energy limit of loop quantum gravity. In other words, spacetime's smoothness is an illusion born of scale, like mist, that when magnified, reveals countless droplets. 2. See how revolutionary this is. Consider what it means for singularities, the infinite densities predicted at the centers of black holes or the Big Bang. In classical relativity, those singularities mark the points where equations break down. But in loop quantum gravity, the quantum structure of space prevents such infinities from forming. Space cannot compress beyond one quantum of volume. That means, in principle, the Big Bang was not a beginning from nothing, but a bounce, a transition from a prior universe that collapsed and then re-expanded. This idea is sometimes called the Big Bounce, and it arises naturally from LQG's equations. NASA's WMAP and ESA's Planck satellites have observed the oldest light in the universe, the cosmic microwave background, giving us a picture of the universe as it was 13.8 billion years ago. These observations match beautifully with the predictions of general relativity, but they can't yet see what happened before that. Loop quantum gravity suggests that before still existed, just governed by quantum geometry rather than classical spacetime. If this is true, then every atom, every planet, and every galaxy is suspended in a vast network of quantum threads. The strength of gravity, the passage of time, even the shape of space, all emerge from the way these loops twist and connect. It's an idea that's as strange as it is logical. After all, we already know that energy and matter are quantized. Why should space itself be any different? Experimental confirmation, however, remains elusive. The Planck scale is far beyond our reach. No telescope or accelerator can probe it directly. But physicists are searching for indirect clues, tiny imprints in the polarization of cosmic light, or subtle irregularities in the timing of gamma-ray bursts that travel across billions of light-years. If space-time really has a granular structure, photons of different energies might travel ever so slightly differently, a fingerprint of the underlying lattice. Such signals are faint, but the tools are improving. NASA's Fermi Gamma-Ray Space Telescope and ESA's Integral mission are scanning the skies for precisely these patterns. So far, space-time appears smooth, but the search continues. Loop quantum gravity stands as a kind of quiet counterpoint to string theory. It doesn't need extra dimensions or new particles. It takes the geometry of space, Einstein's great legacy, and quantizes it directly. Where strings sing, loops weave. And both, in their own ways, whisper the same truth that at the Planck scale there is no such thing as empty space. There is only structure, humming silently beneath the surface of reality. This perspective transforms how we imagine the universe. The cosmos is not a smooth stage where matter performs. It's a living network, dynamic and self-interacting. Matter curves space. Space tells matter how to move. And beneath both lies a hidden architecture of loops and links. And as strange as it sounds, this quantum geometry could be the key to uniting the two greatest theories in physics, quantum mechanics, and relativity without contradiction. A universe built not from particles in space, but from space itself becoming quantum. As physicist Lee Smolin once wrote, "Space is not what it appears to be. It's a network of relationships between quanta, a web that gives rise to geometry when viewed from afar. So what happens if we go even deeper, beneath the loops, beneath the geometry, to where information itself might be the fundamental fabric of reality? What if space-time isn't just quantized but emergent, a byproduct of something even more basic? What if the very thing we use to describe reality, distance itself, is no longer real? What if near and far, before and after, here and there, are only approximations that dissolve when we look too closely? That question marks the quiet edge of modern physics because after centuries of measurement, calculation, and observation, From Galileo's telescopes to the James Webb Space Telescope, we are finally reaching a limit not set by technology, but by nature itself. It began with two separate paths, two independent lines of reasoning that astonishingly both point to the same conclusion. One comes from the gravitational collapse of energy, and the other from the quantum limits of measurement. The first path is purely relativistic. Einstein's theory tells us that energy curves spacetime. When too much energy is concentrated into a small region, the curvature grows so steep that light cannot escape. A horizon forms, the region becomes a black hole. This means that if you try to probe distances smaller and smaller by using higher and higher energies, you eventually cross a threshold where your own experiment collapses into a gravitational well. Beyond that point, nothing, not even information, can return. The act of measuring destroys the very thing being measured. The second path comes from quantum mechanics. Heisenberg's uncertainty principle tells us that every measurement has a built-in fuzziness. The more precisely we try to measure position, the less precisely we can know momentum. This is not a flaw of our instruments. It is a property of the universe. But when we add gravity to that principle, when the measuring photon itself has energy that bends spacetime, something remarkable happens. Increasing energy to sharpen position eventually increases curvature, which blurs it again. There's a balance point where further precision is impossible. This modified rule, the generalized uncertainty principle, tells us that below the Planck length, about 1.616 times 10 to the negative 35 meters, the concept of distance ceases to make physical sense. It is not that we lack the right microscope, it's that the universe itself no longer offers coordinates to define closer or farther. Two different lines of reasoning, one from gravity, one from quantum theory, lead to the same boundary, the Planck scale. At that boundary, Einstein's smooth spacetime and the probabilistic world of quantum mechanics are no longer separate languages. They merge, clash, and demand a new grammar, a unified theory that treats both as equals. That quest to unify gravity and quantum mechanics is the central story of modern theoretical physics. Two great paths have emerged, string theory and loop quantum gravity. String theory proposes that everything, from electrons to spacetime itself, is made of tiny vibrating filaments of energy. These strings are incredibly small, roughly the size of the Planck length. They don't allow infinite sharpness. When you add energy, they stretch and oscillate, never collapsing into a point. Gravity arises naturally from their motion. Loop quantum gravity takes a different approach. It starts not with strings, but with space itself. It treats geometry as quantized, built from discrete loops and nodes called spin networks. Volumes and areas are not continuous but granular, each one a quantum of geometry, roughly the size of the Planck scale. Both theories, though distinct, point toward the same profound conclusion. Space and time are not fundamental. They are emergent, byproducts of deeper relationships. The smooth spacetime we see is like a mirage that appears when countless quantum interactions blend together. At macroscopic scales, galaxies, planets, oceans, and atoms, this mirage works perfectly. GPS satellites depend on it. Light follows it. NASA's spacecraft navigate through it with astonishing accuracy. But zoom far enough down, and the coordinates that guide rockets and photons begin to dissolve. At the Planck scale, a ruler has no meaning and time no sequence. The universe is not here or there, but a web of interactions flickering between potential states. It's a strange place to imagine, yet it might be the birthplace of everything we see. The laws that shaped the first instant after the Big Bang, the inflation of space, the formation of matter, the seeds of galaxies, all trace back to this regime where geometry itself was quantum. NASA's WMAP, ESA's Planck, and now JWST have pushed our observational limits ever closer to that beginning. They can see the universe as it was, hundreds of millions of years after the Big Bang when the first galaxies lit up the darkness. But the true origin, The quantum moment of spacetime's birth remains hidden behind this natural wall of uncertainty. Carl Sagan once said, "We are a way for the cosmos to know itself." But now it seems the cosmos has drawn a boundary around its own reflection. We can observe the stars and galaxies, we can trace the curvature of spacetime, but beyond a certain precision, nature refuses to be seen. It's not a dead end, it's an invitation. Because if distance itself is only an approximation, then physics must find a language deeper than geometry, a theory not of where things are, but of how things relate. In some versions of quantum gravity, that's exactly what happens. Space emerges from entanglement, from the way quantum information is shared between systems. The very act of connection creates geometry. In that view, distance is not a property of the universe, it's an effect of interaction. Space exists because particles exchange information. Without interaction, there is no between. It's a breathtaking thought. At the deepest level, reality may not be made of things, but of relationships. The universe, then, is not a place, but a process. Still, these ideas remain untested. They are maps drawn at the edge of knowledge, beautiful, self-consistent, but waiting for data. And that's where the great observatories, JWST, LISA, and the upcoming Einstein telescope may help. By measuring gravitational waves with extreme precision, they could reveal how spacetime behaves when pushed to its quantum limit. The stakes are enormous. If we can detect signatures of quantum geometry, small deviations in the propagation of waves across billions of chimes, light years, we might finally glimpse the fingerprints of a deeper order beneath relativity itself. But even if that day is far away, one truth already stands. The closer we look, the less we see. Not because the universe hides its secrets, but because the tools we use, space, time, measurement, melt in the heat of their own precision. At the Planck scale, distance is not wrong. It's just incomplete. A convenient language that breaks down when the conversation goes too deep. What lies beyond it may not be smaller or larger, but different. As theoretical physicist Nima Arkani Hamed put it, spacetime is doomed. He didn't mean it will vanish, but that it is only a shadow, an approximation of a richer quantum foundation. And so, after all our measurements and equations, physics arrives back at wonder, at a universe where and when are not the final truths, only patterns that emerge from something deeper, something more fundamental, something still unnamed. What happens when we reach the limit of measurement? When knowledge itself meets its natural boundary? Perhaps then, science does not end. It transforms from measuring to understanding, from mapping the universe to feeling its structure unfold through logic, mathematics, and imagination. And in that quiet realization, the cosmos doesn't shrink. It expands again, not outward, but inward, toward the very fabric of what it means to exist. The deeper we probe into these questions, the more we realize that our journey through physics is simultaneously a journey backward through time. Each energy threshold we cross, each smaller distance we explore, corresponds to an earlier epoch in the universe's history. When we study atoms, we're examining the physics that dominated when the universe was already cooling, when the first elements were forming. When we peer into the nucleus and observe quarks, we're touching the conditions that existed in the first microseconds after the Big Bang. And when we contemplate the Planck scale, we're attempting to understand the very instant of creation itself, the moment when space-time emerged from whatever preceded it. This connection between small scales and early times isn't coincidental. It's fundamental to how the universe evolved. In the beginning, everything was compressed into an unimaginably tiny volume. The entire observable universe, everything we can see today, stretching billions of light years in every direction, was once smaller than a single atom. At that moment, the extreme density meant that the physics of the very small was also the physics of the very large. Quantum effects didn't just matter at microscopic scales. They shaped the entire cosmos. The tiny quantum fluctuations that occurred during the universe's first moments eventually grew into the galaxies, stars, and planets we see today. Every structure in the universe, from the smallest grain of sand to the largest galaxy cluster, carries the fingerprint of quantum mechanics operating at cosmic scales. This is why understanding the Planck scale matters so profoundly. It's not just an academic exercise in pure mathematics. It's the key to understanding where we came from, how the universe began, and potentially where it's going. The laws that govern the Planck scale are the same laws that determined everything that followed. They set the initial conditions for all of cosmic history. Consider what this means for our own existence. The atoms in your body, the oxygen you're breathing, the carbon in your cells, all of it was forged in the hearts of stars billions of years ago. But the laws that allowed those stars to form, that permitted atoms to exist at all, were determined in the first fraction of a second after the Big Bang. And those laws emerged from whatever physics governs the Planck scale. In this sense, we are not just made of star stuff, as Sagan famously said. We are made of quantum geometry, of vibrating strings or loops of space, of whatever fundamental reality underlies the Planck scale. We are the universe's way of examining itself at every scale simultaneously, from the vast to the infinitesimal, all contained within conscious observers trying to understand their own origins. This realization brings a certain humility, but also a sense of wonder. We exist at what physicists sometimes call the middle scales. Our bodies, our world, our everyday experience takes place at dimensions far removed from both the Planck length and the size of the observable universe. We're somewhere in between, neither infinitely large nor infinitely small. Yet from this middle position, we've managed to probe both extremes. With telescopes, we look outward to the edge of the visible cosmos, seeing light that has traveled for 13 billion years to reach us. With particle accelerators, we look inward to scales a billion times smaller than ourselves. This dual capacity for exploration, this ability to transcend the limitations of our own scale, represents one of humanity's greatest achievements. We are small, limited, temporary creatures, yet we can comprehend the infinite and the infinitesimal through mathematics and reason. The Planck scale serves as a reminder of both our capabilities and our limits. We can calculate it, predict it, understand its significance, all without ever being able to observe it directly. This is a different kind of knowledge than empirical measurement. It's knowledge through logic, through the internal consistency of our theories, through the way different pieces of physics fit together like an enormous puzzle. String theory and loop quantum gravity, despite their differences, both point to the same conclusion through different mathematical pathways. They both say that space-time, at its smallest scales, is not what it seems. This convergence gives physicists confidence that even without direct experimental evidence, we're on the right track. The mathematics is too elegant, too self-consistent, too successful at resolving contradictions to be entirely wrong. But mathematics alone cannot give us the complete picture. Eventually, we need observations, experiments, data from the real universe. That's why physicists are so excited about the next generation of gravitational wave detectors, the advanced capabilities of space telescopes like JWST, and potential future experiments that might detect subtle quantum properties of space-time. These tools might not reach the Planck scale directly, but they could reveal its fingerprints. Imagine, for instance, that photons of different energies travel at very slightly different speeds through space due to the granular structure of space-time at the Planck scale. This effect would be extraordinarily small, but over the vast distances light travels across the universe, it might become detectable. A gamma-ray burst occurring billions of light-years away sends photons of many different energies toward Earth. If space-time is truly quantized, the highest energy photons might arrive at a slightly different time than the lowest energy ones. So far, no such effect has been conclusively detected, which tells us that if space-time is granular, The grains must be at least as small as the Planck length, or smaller. But the search continues, and our instruments keep improving. Each null result narrows down the possibilities, constraining theories and guiding us toward truth. Sometimes what we don't find is as important as what we do find. The absence of certain signals can eliminate entire classes of theories, clearing away the wrong ideas to make room for the right ones. This patient accumulation of knowledge, this gradual narrowing of uncertainties, is how science actually works. It's not sudden eureka moments, though those do occasionally happen. Mostly it's careful measurement, repeated experiments, theoretical refinements, and slow convergence toward truth. The Planck scale has been a theoretical concept for over a century. Now, ever since Max Planck first combined the fundamental constants to derive it in 1899, Planck himself didn't fully understand what he had discovered. He simply noticed that when you combine the speed of light, the gravitational constant, and his newly discovered quantum of action, you get natural units of length, time, and mass. He called these the natural units because they didn't depend on human conventions like meters or seconds. They emerged purely from the fundamental laws of physics. At the time, Planck couldn't have known that these units would mark the boundary where quantum mechanics and gravity meet. Quantum mechanics hadn't even been fully developed yet, and Einstein's general relativity was still years away. But Planck had stumbled upon something profound, a hint from nature about her deepest structure. It would take decades before physicists fully appreciated the significance of Planck's discovery. Today, we understand that the Planck scale represents much more than just convenient units. It marks a genuine physical threshold, a boundary in nature beyond which our current theories cannot venture. It's the edge of the map, where the charted territory ends and the dragons of unknown physics begin. But unlike medieval maps, where dragons represented ignorance and superstition, the dragons at the edge of physics represent exciting possibilities. Beyond the Planck scale might lie entirely new phenomena that we can barely imagine. Extra dimensions curled up too small to see. Quantum foam where space-time itself bubbles and froths. Strings or loops vibrating with the fundamental harmonies of existence. Or something completely different. Something no current theory predicts. Something that will force us to revise our understanding even more radically. This uncertainty, this unknowing, is what drives physics forward. If we already knew everything, science would be finished. But every answer raises new questions, every discovery reveals new mysteries. The Planck scale is perhaps the ultimate example of this. We know it's there, we know it's important, but we don't yet know exactly what happens at those scales. That ignorance is not a weakness. It's an opportunity. For young physicists entering the field today, the Planck scale represents one of the greatest challenges and opportunities in all of science. Whoever cracks the puzzle of quantum gravity, whoever figures out how to unite relativity and quantum mechanics, will have achieved something comparable to Einstein's greatest work. They will have unveiled one of nature's deepest secrets, and the solution, when it comes, might not just be theoretical. Understanding quantum gravity could have practical implications we can't yet foresee. When quantum mechanics was first developed in the 1920 seconds, it seemed like pure abstract theory with no practical applications. Today, quantum mechanics underlies all of modern technology. Computers, smartphones, medical imaging, solar panels, lasers, all depend on quantum physics. Similarly, string theory, loop quantum gravity, or whatever theory ultimately explains the Planck scale might someday lead to technologies we can't currently imagine. Perhaps ways to manipulate space-time itself. Perhaps new forms of energy or propulsion. Perhaps insights into the nature of time that could have profound implications. Or perhaps nothing practical at all, just deep understanding of how reality works. That understanding has value in itself. There's also the question of the multiverse. Many theories of quantum gravity suggest that our universe might not be alone. String theory's landscape of 10 to the 500th power possible vacuum states suggests that many different universes might exist, each with different physical laws determined by how the extra dimensions are curled up. Loop quantum gravity's Big Bounce scenario implies that our universe might have emerged from the collapse of a previous universe. Eternal inflation, another framework for understanding the early universe, suggests that universes are constantly budding off from each other in an endless process. In this view, the Big Bang wasn't the beginning of everything, just the beginning of our particular bubble of spacetime. Beyond our bubble, an infinite number of other bubbles might exist, each its own universe with its own physical properties. These ideas seem almost like science fiction, but they arise naturally from serious physics. They're not wild speculation. They're careful extrapolations of well-tested theories into regimes we cannot yet directly observe. Whether any of these ideas are correct remains to be seen. But the fact that they arise so naturally from our current best theories suggests that the universe is even stranger and more wonderful than we've imagined. The Planck scale is intimately connected to all of these ideas. It's the scale where universes might branch off from each other, where the quantum fluctuations that seed new universes occur, where the fundamental parameters that determine physical laws get set. Understanding the Planck scale might ultimately mean understanding not just our universe, but the entire multiverse, if such a thing exists. Even if the multiverse is real, we might never be able to observe other universes directly. They might be forever beyond our observational reach, separated from us by infinite space or fundamental barriers. But even if we can't see them, we might be able to infer their existence through their effects on our universe. Collisions between bubble universes might leave imprints on the cosmic microwave background. Certain patterns in the distribution of matter might hint at the existence of other universes. Physicists are actively searching for such signatures, scanning the sky for any anomalies that might betray the presence of a larger multiverse. So far, nothing conclusive has been found, but the search continues. And even if we never find direct evidence, the mathematical consistency of these theories gives them weight. In physics, theories that are mathematically beautiful and solve multiple problems simultaneously have a tendency to be correct, even when they predict seemingly impossible things. Einstein's general relativity predicted black holes, which seemed impossible at the time. It predicted gravitational waves, which took a century to detect. It predicted the expansion of the universe, which contradicted the prevailing wisdom that the cosmos was static. Yet all of these predictions turned out to be correct. The theory was right because it was mathematically beautiful and solved fundamental problems. Similarly, quantum mechanics predicted that particles could tunnel through barriers, that electrons could exist in multiple places at once, that observation itself could affect reality. All of these seemed impossible, yet all turned out to be true. The lesson from history is that we should take our best mathematical theories seriously, even when they predict things that seem absurd. Nature is often more creative than our imaginations. The theories of quantum gravity, string theory, and loop quantum gravity are mathematically beautiful in the same way that relativity and quantum mechanics were. They solve fundamental problems, they make specific predictions, they might predict things that seem impossible, like extra dimensions or quantized space-time, but history suggests we should take them seriously. One or both might be correct, or they might be stepping stones to an even deeper theory we haven't yet conceived. What's certain is that the journey isn't over. Physics hasn't reached its end. The Planck scale stands as proof of that. There are still fundamental questions unanswered, still deep mysteries to unravel, and that's exciting. It means there's still work to be done, still discoveries to be made, still Nobel Prizes to be won. The universe has not yet revealed all its secrets. For those listening who might be students or considering careers in physics, this is perhaps the most exciting time to enter the field. We stand at the threshold of potential breakthroughs. The tools we have now, both observational and theoretical, are more powerful than ever before. The James Webb Space Telescope is revealing the universe's earliest moments. Gravitational wave detectors are opening entirely new windows on the cosmos. Quantum computers are enabling calculations that were previously impossible. At the same time, theoretical frameworks like string theory and loop quantum gravity are mature enough to make testable predictions. The pieces are in place for potential major discoveries in the coming decades. Someone listening right now might be the one who finally cracks the puzzle of quantum gravity. Who knows? Science advances not through the work of isolated geniuses, but through the collective effort of thousands of dedicated researchers, each contributing their piece to the puzzle. And it's not just professional physicists who can participate. Citizen scientists, amateur astronomers, enthusiasts, and learners all contribute to the broader culture of curiosity and inquiry that makes scientific progress possible. By learning, questioning, supporting science education, and maintaining wonder at the natural world, everyone plays a role in humanity's quest to understand reality. The Planck scale, for all its abstraction, for all its distance from everyday experience, matters to everyone. Because understanding where we came from, how the universe works, what reality fundamentally is, these are questions that touch on the deepest aspects of human existence. They're not just technical problems for specialists. They're questions about our place in the cosmos, about the nature of existence itself. When we look at the night sky and see thousands of stars, we're seeing across space, yes, but also across time. The light from those stars took years to reach us. When we look at distant galaxies, we're seeing them as they were billions of years ago. We're looking backward through time toward the beginning. And at the beginning, at the very start, we find the Planck scale waiting, the moment of creation itself. So, in a very real sense, understanding the Planck scale means understanding our origins. It means understanding the fundamental laws that made us possible. It means grasping, as much as human minds can grasp, the deepest truths of existence. And while we may never directly observe the Planck scale, while it may forever remain beyond the reach of our instruments, we can still understand it through mathematics, through reason, through the beauty and consistency of physical law. This is perhaps the most remarkable thing about physics, that we can know things we cannot see, that we can understand phenomena far removed from direct experience through the power of logic and mathematics, that we can peer into the heart of creation itself, not with our eyes, but with our minds. The Planck scale is testament to this remarkable human capability, and so we return to where we began, to that hard edge at about 1.616 times 10 to the negative 35 meters, the Planck length, where our best laws stop agreeing, where quantum uncertainty collides with gravity, where space-time itself flickers like static. We've mapped this frontier with calm precision, explored what distance means when rulers fail, why energy makes tiny regions collapse, and how atoms, light, and the universe all whisper the same rule. The journey has taken us from the visible world of atoms to the invisible realm of quarks, from the human-built Large Hadron Collider to the natural barrier of the Planck scale. We've seen how light fails where electrons succeed, how protons hide quarks within them, how the universe itself pushes back against our attempts to see too deeply. We've encountered string theory's vibrating filaments and loop quantum gravity's quantum foam, two different paths to the same destination. And we've learned that distance itself, the very notion of here and there, is only an approximation. That at the smallest scales, space-time dissolves into something stranger, something more fundamental, something that our current physics can describe but not yet fully explain. We stand at the edge of knowledge, peering into the darkness beyond, knowing that something profound awaits but not yet able to see it clearly. This is the nature of science. Always reaching, always pushing further, always seeking deeper understanding. The Planck scale is not a wall that stops us, it's a horizon that calls us forward. Beyond it lies either the end of physics as we know it, or the beginning of physics as it will be. Either way, the journey continues. And those who make that journey, whether as physicists, students, or simply curious minds, are participating in one of humanity's grandest adventures. The quest to understand reality at its most fundamental level, the effort to answer the oldest questions. Where did we come from? What are we made of? How does it all work? These questions have driven human inquiry for millennia, from ancient philosophers pondering the nature of matter to modern physicists probing the Planck scale. The questions remain the same. Only our answers grow more precise, more mathematical, more strange, and perhaps that strangeness is the point. Perhaps the universe at its deepest level was always going to be bizarre, always going to defy our everyday intuitions. We evolved to understand medium-sized objects moving at moderate speeds in 3 dimensions of space. We didn't evolve to intuitively understand quantum mechanics, relativity, or the Planck scale. That we can understand these things at all is remarkable. It required us to go beyond intuition, beyond common sense, to trust in mathematics and logic, even when they led us to conclusions that seemed absurd. Quantum superposition, time dilation, space-time, curvature, these all seemed impossible when first proposed, yet nature insists on them. The universe is under no obligation to make sense to us. We must expand our minds to match reality, not expect reality to shrink to fit our preconceptions. The Planck scale is perhaps the ultimate example of this. Nothing in our everyday experience prepares us for the idea that space might be quantized, that distance itself might be an approximation, that there could be a smallest possible length. Yet the mathematics insists on it. Both from quantum mechanics and from gravity, independently, we arrive at the same conclusion, that there must be a fundamental limit to how small we can probe. And so we trust the mathematics. Even though we cannot see it, even though it defies intuition, we trust it because mathematics has proven itself reliable time and again, because equations that are beautiful and consistent tend to describe reality accurately, because logic, applied rigorously, leads us to truth, even when that truth is strange. This is the faith of physics, if we can call it that. Not faith in the religious sense, not belief without evidence, but trust in the power of reason and mathematics to reveal truth. Trust that the universe operates according to laws, not caprice. Trust that those laws can be discovered, written down, tested, and verified. This trust has been rewarded again and again throughout the history of science. And so we continue forward, knowing that the Planck scale awaits, knowing that beyond it lies either confirmation of our current theories or something even more surprising. Either way, we will learn. Either way, human knowledge will advance. And either way, we will be closer to understanding the deepest truths of existence. This is why we do science. This is why we build colliders and telescopes. This is why we spend lifetimes studying equations and seeking patterns. Because understanding is its own reward. Because knowledge is valuable for its own sake. Because humans are creatures who ask why, who want to know how things work, who cannot rest content with mystery when explanation is possible. The Planck scale calls to us precisely because it is mysterious, precisely because it represents the edge of the known, and we, as a species, are compelled to explore that edge, to push it further back, to expand the realm of the known at the expense of the unknown. Each generation does this, building on the work of those who came before. Newton stood on the shoulders of giants, as he said. Einstein stood on Newton's shoulders. And today's physicists stand on Einstein's shoulders, reaching for the Planck scale. Someday, future physicists will stand on their shoulders, reaching for whatever lies beyond. This is the grand tradition of science, each generation adding its contribution, each discovery enabling future discoveries. The path from Newton to Einstein to the Planck scale illustrates how our understanding has progressively deepened. Newton gave us laws that worked perfectly for everyday objects and planetary motion. For 2 centuries, his physics seemed complete. But then cracks appeared. Mercury's orbit didn't quite match predictions. The speed of light seemed independent of the observer's motion. These tiny discrepancies led Einstein to general relativity, which didn't overturn Newton, but rather showed that Newton's laws were approximations valid in the limit of weak gravity and slow speeds. Similarly, quantum mechanics didn't destroy classical physics but revealed its limitations. At large scales with many particles, quantum effects average out and classical behavior emerges. But at atomic scales, the quantum realm reveals itself in all its strangeness. Now we face another transition. General relativity and quantum mechanics both work brilliantly in their respective domains, but they can't both be completely correct because they contradict each other at the Planck scale. Whatever theory replaces them or unifies them won't make them wrong. It will show them to be approximations, valid in certain limits. Just as relativity contains Newtonian mechanics as a special case, and just as classical mechanics emerges from quantum mechanics in the right circumstances, the final theory of quantum gravity will contain both relativity and quantum mechanics as limiting cases. This is how physics progresses, not through revolution but through evolution, each new theory encompassing and extending the old ones. This pattern gives us confidence even though we can't yet see the final answer. We know roughly what shape it must take. It must reduce to general relativity at large scales. It must reduce to quantum mechanics at low energies. It must be mathematically consistent. It must explain the Planck scale. These constraints severely limit the possibilities. There aren't infinite options. Nature has left us clues, and by following them, we narrow down the search. String theory and loop. Quantum gravity both attempt to follow these clues, and both have had partial success. String theory succeeds at incorporating gravity into quantum field theory, at eliminating infinities, at predicting the existence of gravitons. Loop quantum gravity succeeds at quantizing geometry, at eliminating singularities, at deriving black hole entropy. Perhaps one of them is correct. Perhaps both are partially correct, describing different aspects of the same underlying reality. Perhaps both are stepping stones to something even better. The history of physics suggests that when multiple approaches persist despite difficulties, there's usually truth in both. Light behaved like a wave in some experiments and a particle in others, leading to decades of debate between wave and particle theorists. The resolution was wave-particle duality, the realization that light is neither purely wave nor purely particle, but something more fundamental that exhibits both behaviors. Perhaps string theory and loop quantum gravity will eventually merge into a single framework that incorporates the insights of both. Some physicists are already working on this, seeking connections between the two approaches. They've found intriguing similarities, hints that despite their different starting points and mathematical languages, they might be describing the same underlying physics from different perspectives. If this proves true, it would be a beautiful unification, showing that human reasoning can arrive at truth through multiple independent paths. This idea that different approaches can converge on the same truth is deeply embedded in physics. When Maxwell unified electricity and magnetism, he showed that two apparently different forces were actually aspects of the same electromagnetic field. When Einstein unified space and time into spacetime, he showed that two apparently separate things were actually inseparable aspects of the same entity. When the electroweak theory unified electromagnetism and the weak nuclear force, it showed they were low-energy manifestations of a single electroweak force. This pattern of unification runs throughout physics. What seems disparate at first glance proves to be unified at deeper levels. Forces merge, quantities combine, separate phenomena reveal themselves as aspects of single underlying realities. This suggests that the ultimate theory of everything, if such a thing exists, will be remarkably simple and unified. All the complexity we see, all the different forces and particles, will emerge from some elegant underlying principle. The Planck scale holds the key to this final unification. because it's the scale where all forces have equal strength, where all distinctions blur. At normal energies, the four forces, gravity, electromagnetism, weak nuclear, and strong nuclear, are very different in strength and behavior. But as energy increases, they grow more similar. The electroweak unification showed that electromagnetism and the weak force merge at high energies. Grand unified theories suggest that at even higher energies, the strong force joins them, and at the Planck energy, even gravity merges with the others. At that scale, there are no separate forces, just one unified interaction. Understanding that unification means understanding how the universe looked at its very beginning, when all forces were one, before they separated into the distinct forces we see today. It means understanding the fundamental symmetry of nature before it was broken into the asymmetric world we inhabit. This is why theoretical physicists are so passionate about the Planck scale. It's not just about understanding the smallest distances or the highest energies. It's about understanding the fundamental symmetry of the universe, the elegant mathematical structure from which everything else emerges. It's about finding the equation, as Wheeler dreamed, from which the universe springs. The simple principle that generates all the complexity we observe. Whether such an equation exists, whether there's truly a theory of everything, remains to be seen. Some physicists argue that perhaps there's no final answer, that physics might be turtles all the way down, each layer of explanation requiring another layer beneath it. Others counter that the mathematical structure of physical law suggests there must be a foundation, some level where explanation terminates in simple axioms from which everything else follows. This philosophical question, whether explanation has a bottom or continues infinitely, might itself be answered by physics. If we reach a theory that explains everything without requiring further explanation, that would suggest explanation does have a foundation. If every theory we develop seems to require something deeper beneath it that might suggest otherwise, for now, we don't know. We're still climbing or descending, depending on your metaphor, still seeking the foundation or the peak. But wherever that journey leads, the Planck scale marks a crucial waypoint. It's the deepest we can currently theorize with any confidence. Beyond it lies speculation, educated guesses, mathematical explorations that might or might not correspond to reality. At it, and above it, we have theories that work, that make predictions, that connect to observations. The Planck scale is the current frontier, the edge of reliable knowledge. And what a remarkable frontier it is. Think about what it represents. A distance so small that no microscope could ever resolve it, yet we can calculate it. An energy so high that no accelerator could ever reach it, yet we understand its significance. A realm where space and time break down, yet we can describe it mathematically. This is the power of theoretical physics, to explore realms forever beyond direct observation through the power of consistent logical reasoning. The ancient Greeks debated whether reality was ultimately made of atoms, indivisible units, of matter. They had no way to observe atoms, no instruments to detect them, but through reason alone they arrived at a concept remarkably close to our modern understanding. The Planck scale represents a similar achievement. Without ever observing it, we can deduce its existence and its properties through the internal logic of our theories. Whether future observations will confirm these deductions remains to be seen. Perhaps gravitational wave astronomy will reveal quantum properties of spacetime. Perhaps particle accelerators will find unexpected particles that hint at string theory's extra dimensions. Perhaps cosmological observations will detect imprints of the Big Bounce or signatures of the multiverse. Or perhaps the Planck scale will remain forever beyond our observational reach, knowable only through theory. Even if the latter proves true, even if we never experimentally confirm quantum gravity, the theoretical achievement would still be remarkable. Humans would have reasoned their way to an understanding of nature's deepest level without ever directly observing it. That would be a triumph of pure thought, of mathematical reasoning, of logical consistency. It would show that reality, at its core, is rational, mathematical, comprehensible through reason alone. This possibility, that we might understand the Planck scale without ever observing it, raises interesting philosophical questions. Can we truly be said to know something if we can't verify it experimentally? Or is logical consistency and mathematical elegance sufficient? Different philosophies of science give different answers. Empiricists insist that knowledge requires observation. Rationalists argue that reason can access truths beyond experience. Physics, in practice, requires both. We need observation to guide and constrain theory. We need theory to interpret and explain observations. The most powerful physics emerges when observation and theory work together, each informing the other, each correcting the other's excesses. At the Planck scale, we might be approaching a realm where observation reaches its limits, where theory must venture alone. If so, we'll need to be especially careful, especially rigorous in our reasoning. But we'll also need to be bold, willing to follow the mathematics wherever it leads, even to conclusions that seem impossible. The history of physics is full of impossible ideas that prove true. The Earth orbits the Sun, not the reverse, impossible but true. Time is relative, slowing near massive objects, impossible but true. Particles exist in superposition until observed, impossible but true. Perhaps space-time being quantized will join this list of impossible truths. If it does, future generations will look back on our era as a turning point, the moment when humanity finally understood the deepest level of physical reality. They'll study our theories the way we study Einstein's papers and Newton's Principia, as foundational texts that shaped all subsequent understanding. Or perhaps they'll look back on our theories as noble failures, wrong but productive, errors that nonetheless advance the field by ruling out possibilities. Either way, the attempt matters. The effort to understand the Planck scale, regardless of whether we succeed, represents humans at their best, reaching beyond their limitations, seeking truth through reason and mathematics, refusing to accept ignorance when understanding might be possible. This impulse to know, to understand, to comprehend, is among the most admirable of human traits. It doesn't feed us, doesn't protect us from danger, doesn't increase our reproductive success. Yet we do it anyway, because we're curious, because we can't help wondering, because we are the universe trying to understand itself. And in that sense, studying the Planck scale is a profoundly human activity. Not in spite of its abstraction and difficulty, but because of them. We study it precisely because it's hard, precisely because it requires us to stretch our minds to their limits, precisely because it represents the ultimate intellectual challenge. And in rising to that challenge, we become more than we were. We transcend our immediate concerns and connect to something larger, the grand project of human knowledge that spans centuries and civilizations. Every person who has contributed to our understanding of the Planck scale, from Planck himself through Einstein, Heisenberg, Wheeler, Hawking, and countless others, has added their stone to this cathedral of knowledge. And the cathedral isn't finished. It might never be finished. There might always be another question, another mystery, another level to explore. And that's wonderful. It means the adventure continues, means there's always more to discover, always further to go. For those listening who've made it this far through our journey to the Planck scale, thank you. This topic isn't easy. It requires patience, concentration, and willingness to grapple with difficult concepts. But hopefully, you've gained something from it. Perhaps a deeper appreciation for how strange and wonderful the universe is at its smallest scales. Perhaps a sense of awe at what human minds can achieve through reason and mathematics. Perhaps simply the satisfaction of having learned something new, expanded your understanding, added to your mental model of reality. Whatever you've gained, carry it forward, share it with others. Talk about these ideas, wonder about them, let them spark your imagination and fuel your curiosity. because knowledge isn't meant to be hoarded, it's meant to be shared, discussed, built upon. Every conversation about the Planck scale, every moment of wonder at the universe's mysteries, contributes to the broader culture of scientific literacy that society needs. We live in an age where scientific and technological challenges grow ever more complex. Climate change, pandemics, artificial intelligence, biotechnology, space exploration all require scientifically literate citizens who can understand issues, evaluate evidence, and make informed decisions. The skills developed by studying physics, logical thinking, mathematical reasoning, comfort with abstraction, these skills apply broadly. They make us better thinkers, better decision makers, better citizens. So while the Planck scale might seem abstract and removed from practical concerns, the mental discipline required to understand it has real-world value. It trains minds to think clearly, to follow logic rigorously, to distinguish between what we know and what we guess. These skills matter everywhere, in every field, in every life. Learning physics makes us better thinkers, and better thinking makes everything else better. This is the deeper value of exploring the Planck scale, beyond just satisfying curiosity. It develops mental capacities that serve us in all domains. It teaches humility in the face of nature's complexity, while also teaching confidence in human reason's power to understand that complexity. It shows us both our limitations and our capabilities, and in that balanced understanding lies wisdom. And you, listening to this now, are part of that tradition. By seeking understanding, by learning, by maintaining wonder at the natural world, you contribute to the broader culture that makes scientific progress possible. Science is not just what happens in laboratories and universities. It's a way of thinking, a commitment to reason and evidence, a willingness to update beliefs when new information arrives. This mindset, applied broadly, makes all of civilization better. It leads to medical advances, technological innovations, deeper understanding of ourselves and our world. The journey to the Planck scale might seem abstract and removed from daily life, but it's connected to everything. The quantum mechanics we encounter there underlies all of chemistry and biology. The understanding of space-time we gain influences everything, from GPS satellites to our comprehension of the universe's fate. It all connects, it all matters, and it all starts with curiosity, with the simple desire to know, to understand, to comprehend. The Planck scale represents the limit of that understanding with our current physics, but not the limit of curiosity. That will always push further, always seek more, always ask what lies beyond. And that is exactly as it should be. If this quiet journey has brought you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe is more than a gesture. It's a quiet sign that these stories matter to you. And if you'd like, share where in the world you're listening from tonight. Your words, your presence, are like small lights across this dark and endless sky. Thank you for exploring with me. Until next time, rest well, and may your dreams drift gently among the stars.